Again, good afternoon. So this talk was supposed to be given by Jen New. Her visa was rejected, so I have to give the talk. Anyway, I was supposed to be the session chair, so cannot be the session chair because of that. Anyway, so the title of the talk is an improved practical key mismatch attack against NTRU. So I would like to start with explaining the context of the work. So these days, you all know Kyber very well. So Kyber has this CCA security, which means chosen cyber attack. This requirement is very good theoretically, but practically, a better assumption probably is related to what is called key mismatch attack. Why is that? Imagine you are trying to log into Google, right? And you have a public key over there. You use it to do encryption. And in this case, you probably can know immediately if what you sent can be decrypted properly. Because if you can decrypt correctly, you can talk. Otherwise, you should not be able to talk. Therefore, this key mismatch attack is much more practical. So for those lattice-based schemes, actually, the key mismatch attack is actually very subtle. So this situation was in the case of the LW-based scheme was first pointed out by, I think, by Cookland from NSA in 2015, I think. I think Scott also pointed out later. And there was a lot of attacks already on the LW-based schemes for this kind of key mismatch attacks. Actually, those attacks was developed very extensively. I did quite a lot on it, and it become very, very efficient in terms of the number of samples and so on. Okay, and for LW scheme, for Kyber and so on. It was all done. Those attack techniques become very important in the sense that actually, we later realized those people doing side channel attacks on Kyber use that. Same technique. And so this work is actually about NTRU, which means we are looking again the key mismatch attacks on the original NTRU schemes. Okay, there was work done before by the original designer, but the work was a little bit has a very strong assumption. And what we try to do here, this paper is try to fill the gap to see how much we can do in the case of the NTRU. So that's the context of the work. Okay, so I'll start give a little bit more technical details. I think NTRU is pretty well known now. It was designed by Hofstein, Pfeiffer, and Silverman in 1996. So it's one of the first lattice-based public key encryption schemes. It was actually standardized by IEEE, and it was commercialized in some way. I don't know if somebody really used it, but they have this company called Security Innovations. Of course, this one, the original version does not have proven security. So now I'll look at this key mismatch attack before. So this observation already existed in year 2000. Hofstein, Pfeiffer, Silverman, they proposed they call it a reaction attack. It's basically a key mismatch attack against the original NTRU, but they rely a strong assumption on the up-wrapping failures occurred at the one coefficient. I'll explain a little bit in depth later. And then in 2003, Hargrave and so on, they give a reaction attack against the padded NTRU, but in this case, they require a large number of queries. So it's not very efficient. In 2019, in Cincinnati with my students, we also proposed a key mismatch attack, which is related to what we're going to talk about today, but with a probably not optimized number of samples of queries. In 2021, then it successfully mounted a key mission against the HRSS based on searching for optimal binary recovery trees. Okay, and this, we believe the number of queries also become optimal. So what we try to do today is to show you the attack, how you do it with optimal number of queries, and also without the strong assumption given by Hofstein, Pfeiffer, and Silverman at the very beginning. So let's start. And so this is the design of the NTRU scheme. I think most people know. So we have those parameters N, which is the size of a ring, and PQ. P is a small number, and the Q is a large number. They are called coprime. These are two modulars. And then DF, DG, DS describe the number of non-zero terms inside the polynomial. And so this is a ternary system, which means the DF, DG, DS only has 1, -1, and 0. And the public key is given by, this is all known, given by H, which is equal to F inverse times G. Okay, so this is can I point out the point work? Yeah, so this is a public key, H here. Okay, and P times G times FQ inverse modulo Q. And the key thing is the ciphertext. The ciphertext is very much El-Gamal type of design, which is you find something called S, which is also, again, small elements, you times public key, and then add the message. And so if you think about Gamma, the basic idea is you add some noise to your ciphertext, and then because you know the secret, therefore you can remove it. So how do we do that? We first given the ciphertext, you compute this A. So what is A? A is equal to C times F modulo Q, okay? And then in the end, you compute M equal to A times star F inverse Q, okay? So here you have to be very, very important. You have the first modular Q. And then afterwards, then they're small, therefore you can do more than P, therefore require to get the cipher plain text. So that's the basic design. And then let's look, sorry. So let's look at the why it works. Okay, I think this is pretty easy. I will just skip over it. So I don't have to do anything like that. So now let's look at the first key mismatch attack. So what we try to do is to try to modify a good ciphertext such that observe one this decryption fails. That's the basic idea. That's what they do. Okay, so let's look at what original design did. So suppose you have the original ciphertext, which is a valid ciphertext. Okay, what you do, you add some noise into it, which is an integer n times p times x to the ith power. Ith, of course, is one of the monomials. Okay, and then you try to decrypt it. So the observation is very simple. When n is small, probably okay, but when n is big enough, at a certain stage, what? The decryption would fail. Okay, so normally, so what you try to do is to find the first time the smallest n such that the decryption fails. Okay, you can see if you do decryption, you will get what? Now it's Ci times F, so you become C times F, which is A, which I described earlier, and you add this N times P times Xi times F. You notice, right, in the term F, okay, all of the coefficients are either 1, -1, and 0. And then you multiply by M, multiply by P. Xi is not important. You just shift everything. So which means you are A, this is used, the middle product used for decryption will be added by this element. Once you add those elements at a certain stage, when n is big enough, then you will have the one situation what happen is called upper bound overflow, which means you add this together and the one of the coefficients will what? Jump over the modular bound. So which means when you do modular Q, you will do one more modular Q operations. Therefore, your decryption will be incorrect. The same thing happens on the other end, which means if you have something which is go down the lower end of the overflow, which means you have some number less than minus Q/2, then you have to do one more modular operation. Then again, your ciphertext will be wrong. Or it could happen both ways. Okay, so that's what happened. So what the original Hoverstein, Pfeiffer, and Silverman attack, they only consider this case. They assume that all the overflow down at the upper end. Okay, so we want to correct that. That's the number one thing. Okay, and then so what we try to do, remember the key is to find the smallest n. Okay, the key is to find the smallest n. It fails. Okay, and because the circular position of the property of f, therefore you don't care about the exact position. You can find equivalent keys, and what you do, you can use this trick to find the position, and then you can shift it by multiplying xi to shift it, and therefore you find all the keys of the positions for 1 or -1. So that's the basic idea what they did. Okay, so in this paper, so this is what the assumption is. The assumption is what? It's upper bound. So, and we don't really know if it happens all the time or not. So we would like to develop a generic technique to solve this problem. Okay. So in this paper, the attack idea is very simple. So the idea is that instead of just saying multiply MPXI, let me multiply something a little bit more complicated, such that it can help me to what? It can help me to speed up the process to find the coefficients of F. So that's it. So the key idea is what? The key idea is instead of just multiply, instead of just put an n here, you do something different to construct this data. Okay, so that's the basic idea. Okay, and if you observe that if you multiply something in the polynomial case, in this ring case, And then if you multiply, if you express in the matrix form, essentially you multiply this row vector by this matrix coming from a rotation of the coefficients of F. And essentially you are doing a convolution product. So that's it. So this is basically what you will do. Okay, sorry, this is what you will do. And if you look at this number, you realize if they match very well, then you can maximize the sum. Therefore, you can achieve n. Then you can help what to find the mismatches or to cause the decryption failure. Okay, so this is what we do. So in terms of notation, of course, number one, we need to find the smallest integer. And then something else that we define is this t, we can define it to weight, which means given a polynomial, you just add the absolute value together, you choose them as integers, and we would like to use something like this, which means we would like to have a polynomial whose weight, absolute weight is exactly equal to n, then hope user to help us to find the mismatch. So that's the basic notation. And then this lemma, I don't think it's important, it's more technique details. So the framework of the attack is actually pretty simple. So first, choose a ciphertext that can be depicted correctly. Actually, in our attack, we just choose ciphertext to be 0. That's it, nothing else, just 0 in the end. Okay? And then the second step is to find the smallest of n such that this fails, which means I still repeat what it was done before, just find this number n. Okay? And number 3 is we try to construct different t's with this summation of the absolute value of coefficients equal to n, and use that to recover the consecutive sequence of L1, L2, which are coefficients of F, which means just you need one of them, and then you can conceivably find one. That's the basic. Okay, and in the end, of course, through this process, then you do the full recovery. Okay, so and this is the case of going from L1 to LK plus 1 to LK plus 2. I think I will skip this. Let's just look at the simplest case. I think if you understand this one, and that's pretty much it, attack. Okay, so what do you do? Suppose I found the one coefficient L1 equal to 1, just 1. Okay, actually, I mean, we can just assume anyone to be there. And then we'll design T like this. Okay, this is the key. The T will be what? 0, 0, 0, and then m minus absolute value of course just m minus 1, and this will be 1. And then there's another T, which is minus m minus 1 L1. And then if the decryption failure, if you apply T to this, you will immediately know L2 equal to 1. Okay, and then if you get a decryption failure at this number, then you will realize L2 equal to minus 1. Okay, and if it doesn't happen, that means you know L2 equal to 0, because there's no modification there. So that's it. So therefore, by doing this, one bit by one bit, you can just climb up. And similarly, you can do 2 case, and the idea is the same. Okay, so therefore the choice is the smart trick is to what? To design this T and using this formula here, okay, and climb up slowly one by one, just to recover. And I think that's pretty much it. And then for the technical details, I don't think I need to explain. Okay, that's all. And then one more point I already made earlier, which is what? Actually, the easiest way to do is choosing your ciphertext to be 0, which is nothing. And then you can do all the performance and so on, everything works fine. So in the end, I would like to present this table. This table shows the case of NTRU case then. So this Q corresponding to the number of queries. Okay, E is the lower bound on the minimum average number of queries from defined by this previous work actually related to LWE case, which means Kuiper case. Anyway, you have some theoretical bound. For example, here is 739, 742. You can see we achieve essentially the theoretical bound, what we know now, attacks. So that's it. And then of course, I did not do it. So I think she did all the experiments to verify everything. That's it. That's all the work. Okay, we have done. So which means you can push what was done before on the key recovery attack, a mismatch attack on all the previous LW time schemes to the NTRU scheme. They're the same, essentially. Okay. Okay. And I think that's it. That's the talk. And that's the summation of what is done. I already explained to you. I think that's it. Basically, just extend the key mismatch attack from previous cases to the NTRU case and show it works. And it can be done efficiently. Okay, thank you very much. My
Thank
time
you.
is over. Thank you.
Any questions, comments?
Okay, the NIST version, the version of NTRU which was submitted to the NIST competition actually includes some checks for this. Does those checks invalidate this attack?
Sorry, I don't remember details. If they claim CCA security, of course.
Okay.
Yes, I think they claim CCA security, yes. Yeah, I believe so, yes.
Thank you for the good talk and excellent work. My question is probably is not only for this work, but related. In this key mismatching attack, there are a lot of different versions, but what do those attacks actually means to the entry and even to the other attacks?
So I can give you.
They are going to be in the standard, and we're going to be used.
Oh, no. I think.
Is there any?
No. This will not. I mean, so this attack only shows the significance of a CCA security. You have to require, because otherwise I can perform. Not the CCA. CCA is kind of unrealistic, right? It's a theoretical assumption, right? You can get a decryption oracle to decrypt any message you want, but you don't need it, right? In the case of TLS, for example, key mismatch is very practical attack. So you can mount it easily. So what this shows that the additional measures taken by Kyber and so on. For example, Kyber, if you look at Kyber, I think as a program, you will be very frustrated. I decrypt message, but I have to do what? I have to re-encrypt the whole thing again to make sure it matches exactly the ciphertext. So if you don't understand it, then you would just say, let's just ignore it, right? I just decrypt and then we're done, you're dead. So I think that's the key. This just convinces us you have to do this part. Yeah, so this is also very important. But one more thing very important, I realize, in the case of Kyber, and if you're interested in hardware attacks, right? So we run this re-encryption process. In the end, we make a decision, yes or no, right? So if you do injection attack, imagine if you just block that bit to convert that bit into yes all the time, then you are in trouble. So it's very important from this attack, you realize you have to protect that part very carefully. So practically, I think this is quite important. And also very interesting is this, at least for the Kyber case, the technique developed for key mismatch tracking used in the side channel attack. So this is all the same technique by now. So that's what is the practical implication.
You recommend if anybody implement Kyber,
yes, you have to be,
so you need to be careful.
Yes, you need to be very careful. So this
like avoid any side
yes,
channel
yes.
attack, also avoid
Yes.
this type of attack.
Yes,
Yeah.
I mean this attack didn't exist. I mean CCA of course exists for ISA so on, but this key mismatch attack to mount on ISA is not so easy. You know what I mean? Because over there all the bits are. In the case of ISA, all the bits are bind together. You cannot separate them. Here you can see I can get each coefficient separately, but in the ISA case you can. So it's much easier in some sense. Yeah. Okay. Thank you.
Any further comment or question? If not, thank you very much.
Okay.
Again.
Thank you. Thank you.